Okay. Hi, everyone. Well, first of all, I want to thank organizers for organizing this very wonderful event. So today, I'll talk about hybrid quantum classical search algorithms. Okay, so what is search? So we'll consider search, or more precisely, unstructured search, in an oracle setting, where we are given access to some n-bit string, which we initially know nothing about. So given an index I, an oracle tells whether xi is equal 1 or not. And our goal is to find I such that xi is equal 1. And we will call such indices I marked. And for a problem to make sense, we assume that at least there is one marked index. Okay, so before I talk about hybrid oracles, let me talk about purely classical and purely, but before I talk about hybrid algorithms, let me talk about purely classical and purely quantum algorithms. So in a classical setting, we can assume that we have our own classical device, which knows initially nothing about input x, and it can interact with an oracle, which we can assume it to be some very powerful, quick device, which tells us for every index I, what is xi. And similarly, in a quantum setting, purely quantum setting, we can assume that we have our quantum machine, which interacts with a quantum oracle. And one of the, maybe I think the main advantage of the quantum oracle is the ability that we can query it in superposition. However, there might also be some advantages for the classical oracle, especially if you think about more practical settings. And that is that, suppose that we can think of xi as being some function of I that the oracle is computing. And it's computing it using some procedure. And we can assume that the classical oracle and the quantum oracle is using the same procedure for computing this xi. However, it's reasonable to assume that the classical oracle has much higher clock rate, and therefore it can execute these queries much quicker. So, so the question is, can we get the best of the both worlds? We know that because of the ability to query in a superposition, quantum algorithms can solve search using quadratically less queries, but the question is, can we take a lot of those queries and substitute them by a lot of those quantum queries and substitute them by the classical ones? And that is the reason why we introduce hybrid algorithms. So for hybrid algorithms, we consider having our quantum device to have access to both classical and quantum oracle. And of course, we have to ensure that our quantum device doesn't query the classical oracle in superposition. So we have to introduce some kind of interface between the two systems, which we can assume just to be a measurement on the computational basis of the classical oracle. Okay, so now before I formalize this model any further, let me talk about what is the research question that we are interested in here. So suppose that we have C queries to classical oracle and Q queries to quantum oracle. So we know that if you have a purely classical search, then the best we can do is that we need to perform linear number of queries. And for purely quantum one, the best we can do is that we have to perform a square root of n queries. And the question is, is there a hybrid search algorithm that uses asymptotically strictly less than a square root of n quantum queries and asymptotically strictly less than a linear number of classical queries? And before I pose question 2, which will be a more extreme question, let me mention that for some problems such trade-offs exist. And for example, for collision problem, in which we have a random function from n elements to n elements, the task is to find a collision, and there we know that the best classical algorithm has complexity square root of n, the best quantum algorithm has complexity cube root of n. However, there are also hybrid algorithms which uses for which the number of quantum queries is strictly less than cube root of n, the number of classical queries is strictly less than square root of n, yet this algorithm can still solve collision with close to constant probability. So constant probability. Okay, so now, so there might be some hope that maybe something similar happens to search. So going back to the search, so the second question is just even more extreme, and this is up to best of my knowledge, but sometimes best of my knowledge is not that good, is that if I just give you one quantum query and square root of n classical queries, that as far as I can tell, it was not even known that in this setting it was shown that this kind of search is not possible. But it seems like it's too much to hope, and indeed it is. And so what I showed that the answer to both of these questions, 1 and 2, is no. So the main result is the theorem 1, which says that search requires at least a linear number of classical queries, or at least square root of n quantum queries. So what this result essentially says is that if somebody comes along and gives you some amount of classical query resources and some amount of quantum query resources, what you can do, and these resources are enough to perform search, then you can just, it will be enough to take one of those two resources to perform search. So there's never really any advantage of using both of them. So this theorem concerns the scenario when we want a success probability to be close to 1. But we can also consider a small success probability scenario where, we are just given some number of classical queries and quantum queries, and we want to see how well we can do. And for that, I also can show the tight bounds that, if the best success probability that you can get is C over n plus Q squared over n. And, it's quite easy to see that theorem 2 fully encompasses theorem 1. However, the nice thing about theorem 1 is that its proof is much simpler. Okay. So now I'll talk a little bit about, I'm going to formalize a little bit our model of computation. And when I'm going to formalize this model of hybrid algorithms, I will make some simplifying assumptions about the model. However, these simplifying assumptions are specially tailored for search, meaning that for search, these assumptions are without loss of generality. So for the quantum oracle, what we will take is we'll just take the phased oracle, which is the oracle we typically consider when, for example, analyzing grower search. So for index I, what we do is we apply phase -1 if and only if xi is equal 1. And also, we can call this oracle in the superposition. As for the classical oracle, even if our quantum algorithm tries to call it in a superposition, what we first do is we non-destructively perform the measurement on the computational basis states. And then we just get one index, and what we do is we just return this one index, and in addition, we output bit xi. Okay. And now, because we are concerned with a search problem, we can make some additional simplifying assumptions. And in particular, so if this output bit xi is equal 1, then we know that whatever we have in this other register is the answer to a problem. And we can just terminate, and just rejoice, and we are done. However, if xi is equal 0, then we have to continue. And now, what I'll do is, I'll start kind of already working towards the proof of our results. Is I will actually not going to use a classical oracle, but I will use a slightly more powerful oracle in my proofs. And because I'm going to be proving hardness using a more powerful oracle, it means that all the results will also carry over for classical oracle. And that's the oracle that I call pseudo-classical oracle. So it's very similar to the classical one, except now, instead of performing measurement on every single basis state I, we just perform non-destructively perform two outcome measurement specified by projectors pi1, which projects on all indices I such that xi is equal 1, and pi0, which projects on all indices I such that xi is equal, pi0 projects on all indices I such that xi is equal 0. And in addition to this projection, we also output this, one bit which corresponds to the measurement. And as before, if our measurement outcome is 1, then we can just, rejoice and go home. We are done. Okay. So now, how a generic algorithm would look like for generic hybrid algorithm would look like? Well, it is specified by 3 things, and all of them are independent from the input x. So the first thing is initial state chi0. The second is a fixed order of oracle calls. So in this particular example shown here, it's pseudo-classical, quantum, pseudo-classical, pseudo-classical. So I already done this thing where I substituted my classical oracle calls by pseudo-classical oracle calls, because they are at least as powerful as the classical ones. So we will prove hardness for them, and the hardness will carry over for classical. And the third thing for specifying the algorithm is some input independent unitaries U0, U1, and so on. So, and how the computation proceeds, it starts with this initial state chi0, and then we alternate between applications of unitaries and oracle calls. And again, I want to mention once more that whenever pseudo-classical oracle call says 1, we can just stop. Okay, so now I'll talk a little bit about what would be the hardest inputs for search. So when we are looking for the marked index, it makes sense that the hardest inputs are the ones where there's only one marked index. So the hardest inputs for these inputs of Hamming weight 1, where there's only one marked index, we will show that the problem is hard, and it means that it's hard in general. However, we will also consider all zeros input. Of course, here there are no marked elements, but this input is nevertheless very convenient to study. Essentially, the reason for that is because there's close similarities between unstructured search and evaluating the OR function. And one thing that is very convenient for this input is that if you think of the pseudo-classical oracle for this particular input, then it always outputs 0. So essentially, it keeps the state of the computation always pure. Okay, so now let's go back to our circuit diagram of our algorithm. And now what we will do when trying to see how, we will look at the various stages of the algorithm, and we will try to somehow look at the state of the algorithm at these stages, and using these states somehow evaluate how much our computation has progressed towards solving the problem. So we will look at the states right after every oracle call. So at the very beginning of the algorithm, independently of what input we consider, we always have a state chi0. Okay, so now let us focus on this all 0 input. So for this input, what happens is, as I mentioned before, pseudo-classical oracle calls always just act as identity operation, and therefore, when we look at these states after every oracle call, they will be pure states. So there will be some vectors of unit norm. And I'm going to denote the state just after oracle call number t by phi t. Okay, so now let's look at the inputs of Hamming weight 1. So what happens now is that it may happen that pseudo-classical oracle sometimes returns 1. But as I mentioned, in that scenario, we can just terminate the computation and go home and celebrate. So when I'm going to be defining the states of the algorithm after oracle call, I will focus only on a branch of computation where so far all the pseudo-classical oracle calls have returned 0. And so there was this projective measurement inside every pseudo-classical oracle call. So when defining these states, I'm going to assume that I do not renormalize them after that measurement. So essentially, that will mean that when we have these states, I'll have their norm squared will be equal to the probability that we have reached that part of the computation. So in general, their norm might over the time reduce, and it might also change its angle with respect to phi t. So here by psi kt, I denote this state just after oracle call number t. And now using these states, we can define the following progress measure, which was already considered in a work by Regev and Schiff, where they considered search with certain type of noisy oracles. This same progress measure, almost the same progress measure, turns out to work also here for proving theorem 1. And so how do we define it? We take these two vectors, psi k t and phi t, and take their Euclidean distance between them squared. And so for every k, we define this individual progress measure. And here I have an illustration. If I fix state phi, and then I can draw these contour lines which show the values of age for various states psi k. And then once we have these individual progress measures, we can define the overall progress measure as just their average. And now, having this progress measure, essentially the theorem 1 follows from 4 observations. First, that the initial value of the progress measure is 0. The final value has to be at least close to 1 in order for the error to be small. Then, we can show that one call to pseudo-classical oracle cannot increase this progress measure by more than 1 over n. And one call to quantum oracle cannot increase it by more than 4 over square root of n. And then it's quite easy to see that, by just combining these all 4 points, we get theorem 1. I'm not going to go into much detail how do we actually prove these points, but the idea is something like this. If you think of having all input, all 0 string, and we look at the state just before oracle call, we can see how much probability weight this state places on querying index k, and essentially that probability weight will be what contributes to change in this individual progress function hk. And then using our regular friends as Cauchy-Schwarz, triangle inequalities, and so on, we just get these bounds. Okay, so now I'll just briefly mention a little bit about theorem 2, which is, as I said, this result encompasses theorem 1. And for this theorem, we can actually provably show that this progress measure that we considered before, it doesn't work anymore. Using that progress measure, we cannot prove this theorem. So what we do instead, that now we introduce this time we need to introduce 2 progress measures, A and B. And again, we start with individual progress measures for every k, and then take their overall progress measures by taking their average. And again, these progress measures are defined using these states psi k and phi. And just like for theorem 1, we can tell something about the initial values of these things, something about how these progress measures relate to success probability. We can bound by how much they can change by quantum queries and by how much they can change by pseudo-classical queries. One thing that makes, unlike for theorem 1, we are not done here because it still takes some, because now we have two progress measures, we have to, consider various trade-offs. For example, if we are willing to reduce progress measure B by a lot, then that might also reduce progress measure A by a lot, which is actually what we want. And so there's still a little bit of work to be done here. After still doing a little bit of work, we can get theorem 2. So just to conclude, so this is the summary of my results, the 2 theorems that I've shown. And also I want to mention some recent developments, which were still left as open questions in my paper, and most notably the result by Hamoudi, Liu, Sinha, which showed tight trade-offs for collision problem in the hybrid model by providing the upper bound on the success probability. And with this, I would like to thank you for your attention.
Thank you. Questions for Ansis?
So this lower bound technique with a progress measure is reminiscent of some interpretation of the adversary bound. Can you reformulate? Did you try to reformulate your bound as some kind of variation of the adversary bound using the similar formulation?
So So this first follow-up result that I mentioned, they are using something essentially similar to this genres recording oracle technique. And that technique itself is a little bit similar to adversary bound. So that would be one way maybe to how to get it closer to adversary bound. If we just have adversary, I don't know if there's like off-the-shelf adversary which would handle classical queries, but yeah, maybe through this genres approach, like as they did actually, maybe that can be made even closer to look like adversary bound.
Other questions?
Yeah, I guess it's kind of self-promoting, and answering a question, I feel the oracle you consider is very similar to the bump query I considered in my previous work, because you have like a query that when you hit one of the value and the algorithm just end. And yeah, so that's very similar to the bump query I considered before, and we had. But we only have those query, and we don't have a mixer of the queries, so I don't know how that works out. But we do have adversary like bound there, so maybe that's something you consider or can be done.
So that is this bomb testing model, or?
Yeah.
Yeah. I haven't really thought about that connection, but it's. Yeah, I think it would be, I should revisit it and see if there's if I can see some nice overlaps there. Yeah, it's interesting. It's a good suggestion.
Other questions? If not, then I have a question. So you say you couldn't use the Regef-Schiff measure to get your result C plus Q squared over N, but it looks like if you look at your proof of theorem 1, you immediately get another upper bound which is sort of qualitatively the same, namely C over N plus Q over root N. Isn't that sort of effectively the same thing? Because, either the C over N or the Q squared over N are going to dominate your expression, and then you're back at what you get immediately from Regef-Schiff.
Well, so that is true that from theorem 1 we get the Q over square root of N.
C over N plus Q over square root of N.
Yes. But we kind of know that this, let's see. I think it doesn't necessarily, because, for example, then if I say that I give you one quantum query and one classical query, such a lower bound would still not rule out success probability 1 over square root of N.
Oh, I see. Yeah, that's
right. But in reality, yeah.
Yeah, I think if you look at success probability at least 2/3, then the two formulations would be.
Oh, yeah. So this second one is like when we look at when we don't have essentially sub-constant success probabilities. Yeah.
Thanks. Okay, if nobody else, then let's thank Ansis again.